Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Fracture of Ceramics from the paper Ceramics. So the learning objectives of this module are: first, a brief discussion of the stress intensity factor and design with pre-existing cracks. Second, in some cases, the stress intensity factor is not constant, but it depends on the crack size. So we'll study this R curve behavior. Third, the fracture roughness or toughness testing. Lastly, we will study about the statistical aspects of fracture. So students, let us start with a brief introduction about the module. The ceramics, which are used in applications where their mechanical properties are important, are called as structural ceramics. So mechanical properties include strength, modulus, resistance to fracture, creep, wear resistance, etc. So ceramics tend to fail by brittle fracture. This is the most important factor limiting the use of ceramics in structural applications. So resistance to brittle fracture is therefore the most important property of ceramics. So in this module, we will saw how the ceramics fail in a brittle manner. The actual length is approximately 10 to 100 of theoretical strength. This is because of the presence of pre-existing flaws. So two approaches to treat the problem has been discussed. First, the energy balance approach, and second is the mathematical crack approach. The latter yielded a parameter called as the stress intensity factor at the critical value of which the fracture occurs. Ductile and brittle fracture. So students, the physical operation, the separation of a component into two or more pieces is termed as fracture. In general, if a metal specimen is deformed in a tensile machine, it undergoes substantial plastic deformation as manifested by reduction in its cross-sectional area and elongation of its gauge length. Such a fracture is called as a ductile fracture. In other materials, such as glass, there is no significant plastic deformation before fracture. Such a fracture accompanied by little or no plastic deformation is called as brittle fracture. In addition to glass, which is an amorphous material, the brittle fracture can also take place in crystalline materials such as ionic solids, ceramics, BCC and HCP metals at low temperatures, and polymers below their glass transition temperature. Theoretical fracture strength. So assuming that the brittle fracture occurs by the rupture of atomic bonds, an estimate of the stress required for brittle fracture can be obtained. So, this figure shows schematically the atomic bonds in a crystalline solid being stretched due to an applied force. So, here the situation for a single bond is considered. Now, this below figure shows the change in potential phi as the distance between the atoms changes, while the lower figure shows the stress as a function of separation between the atoms. The stress can be approximated by a sign function as sigma equal to sigma max sine of pi multiplied by A minus A naught by Am. Here sigma max is the maximum stress reached during bond stretching before the bonds break. That is, it is the fracture stress. A naught is the interatomic separation and Am is as shown in this figure. When the bonds break, a fracture surface is produced. The work done in bond breaking is the energy of the new surface created. As the two fracture surfaces are created, we have 2 gamma equal to sigma max multiplied by integral A naught to A naught plus Am over sine of pi multiplied by A minus A naught by Am multiplied by dA. So this is equal to 2 Am by pi multiplied by sigma max, where Am is pi gamma by sigma max. So for smaller strain, epsilon equal to A minus A naught by A naught and sigma equal to sigma max pi multiplied by A minus A naught by Am. This is equal to sigma max multiplied by pi A naught epsilon by Am, which is of the form sigma equal to E epsilon, where E is the Young's modulus. Thus, E equal to sigma max multiplied by pi A naught by Am, or sigma max equal to pi A naught divided by pi gamma multiplied by sigma max. Or we can say sigma max equal to root of E gamma by A naught. So using the typical values of gamma, sigma max equal to E by 10. For the polycrystalline ceramics, E is equal to 100 to 500 gigapascal. So the theoretical fracture stress sigma max should be between 10 to 50 gigapascal. Usually it is 100 to 500 megapascal, that is less by the factor of 100. Pre-existing cracks cause brittle fractures. So large discrepancy between the theoretical and measured strength. A variation in the strength of a given set of samples by a factor of 2 or more. The strength is smaller for a larger sample size. Griffith's ideas are: first, there are pre-existing cracks on the surface of the glass sample. Second, the cracks produced due to handling, usage, or even during the storage. Third, there is a distribution in crack sizes or severity of the crack on the surface of each sample. So on loading, the most severe pre-existing crack propagates and causes the fracture if the decrease in the elastic strain energy due to its propagation is at least equal to the energy required to create the new crack surface as a result of fracture. So in ceramics, the cracks can also be in the interior. The crack size in ceramics usually scales as the grain size. Quantitative treatment of brittle fracture. The fact that the fracture in the brittle solids initiates from the most several flaws, and there is a distribution of the severity of these flaws in a given piece, and further that this distribution varies from piece to piece, raises the question where there is any inherent property of the material which can be measured and would give an idea of its behavior in brittle fracture. So students, there are several approaches available for quantitative treatment of brittle fracture. One of these leads to the concept of stress intensity factor, which has been found useful for the designed purpose. So in the following sections, the two approaches for the quantitative treatment of brittle fracture will be discussed. Treatment of the Griffith crack, that is the energy balance approach. Consider a plate in which there is no crack, which is loaded to a uniform stress sigma. The elastic energy per unit volume in the plate is then sigma square by 2E, where E is the Young's modulus. Now introduce A through the thickness crack of length 2A in the center of the plate. So the stresses in the plate in the neighborhood of the crack relax because of the presence of the crack. The relaxed zone on both the sides of the crack can be approximated by a triangular shape of height beta A. That is, in this zone, the stress is 0. Then the relaxed volume to the right of the y-axis equal to beta A square T, where T is the thickness of the plate. It is reduced in the stored elastic strain energy per tip equal to sigma square by 2E multiplied by beta A square T. So the energy released, which is reduced due to the introduction of the crack per unit thickness per tip, equal to sigma square by 2E multiplied by beta A square. So the accurate relation by Griffith gave this quantity to be U equal to sigma square by 2E by pi sigma square by 2E multiplied by pi A square. Griffith crack, the energy balance approach. So increase in the energy due to the creation of the new crack surface per tip equal to 2 gamma A. So total energy change T equal to 2 gamma A minus sigma square by 2E multiplied by pi A square. So the change in the total energy as the crack length increases by an incremental amount dA equal to dt by dA equal to 2 gamma minus sigma square by E multiplied by pi A. So when A exceeds a critical value A star, there is a decrease in the energy with further increase in the crack length. That is, the crack propagates and the fracture occurs. So at this point, dt by dA equal to 0. It is equal to 2 gamma minus sigma square by E multiplied by pi A. At this point, dt by dA equal to 0 equal to 2 gamma minus sigma square by E multiplied by pi A, or 2 gamma equal to sigma square by E multiplied by pi A. So the right hand side of this equation is called as the crack extension force and is denoted by G, which is equal to sigma square by E multiplied by pi A. So here G, for the crack to extend, G must be greater than equal to gamma. So as shown in this figure, which shows that the change in the surface energy 2 gamma A, stored elastic energy U, and the total energy as the crack advances. So energy consuming events are: first, surface energy of the new crack surface is created. Second, the generation of micro cracks and other events. Third, in metals, there is a plastic deformation. So we replace gamma by R, the crack growth resistance is obtained. So then, for the crack to advance, G is very much greater than equal to R. So this figure shows schematically the change in G with the increasing stress with pre-existing crack of half length A. So at a stress equal to sigma F, G exceeds R and the fracture occurs. So at this point, GC equal to sigma F square by E multiplied by pi A. We can also write root of sigma GC multiplied by E equal to sigma F multiplied by root of pi A. So the term on the left hand side is a function of the properties of the material, while that on the right hand side depends on external variables. Griffith crack, the stress intensity factor approach. This approach has turned out to be the most useful as it provides a directly measurable quantity which can be used for the design purposes. In this approach, a mathematical infinitely sharp crack of length 2c is considered. The stresses near the tip of such a crack can be calculated by the elasticity theory. The stresses on element located at a point P near the crack tip are given by the following expressions, that is sigma x equal to sigma multiplied by root of c by 2r multiplied by cos theta by 2 multiplied by 1 minus sin theta by 2 sin 3 theta by 2. Sigma y equal to sigma multiplied by root of c by 2r multiplied by 1 plus sin theta by 2 sin 3 theta by 2. Sigma xy equal to sigma multiplied by root of c by 2r sin theta by 2 cos theta by 2 cos 3 theta by 2. So here sigma z equal to 0 for plane stress and sigma z equal to nu multiplied by sigma x plus sigma y for plane strain. So this figure shows us the three modes. Mode first is the stress intensity factor. Mode first refers to the case when the stress is applied perpendicular to the crack surface. In mode 2 and mode 3, the stress is applied parallel to the crack surface, producing a shear loading and a tear loading respectively. So, in terms of KT, the various expressions for stresses near the crack tip assumes the form sigma x equal to Ki divided by root of 2 pi r multiplied by f theta. Ki equal to mode I stress intensity factor equal to fracture toughness. So earlier we saw that the critical energy release rate for the fracture is Gc equal to sigma c square by E multiplied by pi A. So this can be written in terms of Ki as Gc equal to sigma c square by E multiplied by pi A equal to Kic square divided by E. So this implies that the fracture would occur when the Ki reaches a critical value Kic, since the energy release rate would reach the critical value for fracture. So the quantity Kic is called as the critical stress intensity factor or the fracture toughness T of the material. Stress intensity factor. So, for a mathematical crack, the stress intensity factor is defined as Ki equal to sigma multiplied by root of pi A, where sigma is the applied stress and A is the half crack length. This was defined for the case of an infinitely sharp mathematical crack. For real situations, the stress intensity factor depends on the geometry of the cracked configuration. The stress intensity factors for some common geometries are also available. For others, several approaches are available, some of which may be quite time consuming. So, for a body with a through the thickness crack of length 2a, the stress intensity factor is given by Ki equal to y multiplied by sigma multiplied by root of pi a, where y is a factor which depends on the dimensions of the sample and the loading geometry. R curve behavior, stable crack growth. Defined are the crack growth resistance as the energy required for the crack to advance. Fracture occurs when the stress is increased and G, the rate per unit increase in crack length of the release of energy, equals or exceeds R. So R is usually independent of the crack length, and the fracture, once started, goes to completion as G equal to sigma I square pi A by E increases with the crack length. So in the above treatment, R is assumed to be independent of the crack length. So this is the case, for example, when the size of any energy dissipating process zone ahead of the crack tip does not change as the crack advances. So if the size of the process zone increases with the crack length, then R will also increase. If R has become larger than G at any point, the crack stops. So an increase in the stress is needed to continue the crack growth, and this is known as stable crack growth. Case that is R increases non-linearly with the crack length. So here the top figure shows the energy release rate G and crack growth resistance R versus crack length A. R is constant with respect to A, so cracks of half lengths A1 and A2 will extend unstably when the stress is raised to sigma 1 and sigma 2 respectively. The case 2 is GR increases non-linearly with A. So more illustrative to plot delta A, the increase in the crack length, rather than A on the x-axis. The initial crack lengths are indicated on the left side on the x-axis. So as the 2 gamma is very much less than other energy dissipating terms, r can be taken to start from the origin at delta A equal to 0. So initial half length A1, when sample loaded to stress say S1, G reaches to G1. This implies the pop-in and the crack length increases by a small amount D, the capital D, multiplied by A1. So G becomes less than R and so the crack stops. Fracture toughness testing. Now various geometries of the test sample have been designed for the determination of the critical stress intensity factor KIC. This quantity is called as fracture toughness. A very simple and a common geometry is that of a bar of the material with a rectangular cross section tested in 3-point bending. The sample dimensions and the loading geometry is shown in this figure. So for this case, the geometric factor is given by the polynomial expression for the case when L by H equal to 10. This expression is y equal to 1.93 minus 3.07 multiplied by C by H plus 14.3 multiplied by C by H the whole square minus 25.11 C by H the cube plus 25.8 C by H the power 4. Identation fracture toughness testing. So a Vickers identer is used to ident the surface. The indent made on the surface is shown on the lower figure, and the above figure shows the Vickers indenter. Now here the cracks are formed at right angles to the surface, which are semicircular in shape, and these are called as median radial crack. Lateral cracks, which are parallel to the surface, are also formed. So the fracture toughness is given by Ki equal to chi to the power p divided by c to the power 3 by 2, where p is the load used to make the indent, c is the half crack length, chi is a parameter depends on the material and the indenter, which is given by chi is equal to b multiplied by root e by h, where e is the Young's modulus, h is the hardness, and beta is a parameter determined by calibration test. Statistics of brittle fracture. The distribution of crack lengths varies from sample to sample. So the above figure shows schematically how the crack length distribution may appear. As the length of the largest crack present in a group of samples from the same ceramic may vary widely, their strength will also have a distribution. So in the brittle materials, the scatter in the fracture strength is quite wide, unlike the case for, say, metal specimens where the scatter in the strength is very little. So a simple average of the strengths in the case of brittle solid is not of much use. So since the strength depends on the extreme values of the crack length in a sample, it implies that the strength of a group of otherwise similar samples will have a distribution similar to the distribution of the extreme value of crack lengths in the group. So one of the statistical distributions which is to be followed by the extreme value of the crack lengths in the brittle solid is Weibull distribution. When the samples are all of the same volume, then the following simple two-parameter form of the Weibull distribution can be used. So P as a function of sigma f equal to 1 minus exponential of minus sigma f by sigma naught to the power m. Here P sigma f is the probability that the sample falls at a stress less than equal to sigma f, and sigma naught and sigma and the m are the parameters of the distribution. So the change to ln of minus ln 1 minus p sigma f equal to m ln f minus m ln naught. So the plot of ln of minus ln 1 minus p sigma f versus ln f is a straight line whose slope gives m and the intercept gives minus m ln naught, where m is a shape parameter. Large M corresponds to steep curve, corresponds to strength distributed in a narrow range, more reliable material. M small corresponds to curve spread, more scatter, less reliability as shown in this figure. So the value of M high is around 100 for metals and low around 5 for ceramics. So students, let us summarize what we have learned in this module. First, the ceramics are attractive as structural materials because of their high temperature resistance, corrosion resistance, wear resistance, and high modulus. Second, their major drawback is their brittle nature. Third, the theoretical fracture strength of brittle solids can be calculated and comes out to be of the order of E by 10, where E is the Young's modulus and the actual fracture strength is lowered by a factor of 10 or more. Next, the reason for this, as found by Griffith, is the presence of pre-existing flaws such as cracks in the brittle solids. So when a sample of such a material is loaded in tension, most severe of these flaws propagates at a stress much lower than the theoretical strength and causes fracture. So two approaches to quantitative treatment of brittle fracture were discussed. Next, the energy balance approach was discussed, which gives us the criteria for a crack to grow simultaneously and for the fracture to occur is that the decrease in the strain energy must be at least equal to the new surface energy created. The minimum amount of energy required to be released per unit advance of the crack tip is called the energy release rate, GIC. This approach gives a valuable insight into the fracture process, but it is difficult to use this idea quantitatively for the design purposes. Next, we discussed about the stress intensity factor approach, which is more useful and can be used for design. A mathematically sharp crack in an elastically stressed body is considered. The stresses in the vicinity of the tip of such a crack can be calculated exactly from the elasticity theory. So the expressions for various stresses in the vicinity of the tip contains a factor Ki equal to sigma root of pi c, where sigma is the nominal stress and c is the half crack length. Now this factor Ki is called the mode I stress intensity factor. Similar intensity factors can be defined for mode 2 and mode 3, in which the stress is applied parallel to the crack surface in the shear mode and in the tear mode respectively. Most common is mode first. For mode first, Ki and Ji, they are related by the relation GIC equal to KIC square divided by E. So fracture occurs when the value of G reaches a critical value GIC or when Ki reaches a critical value KIC, called as the mode first critical stress intensity factor or the fracture toughness T of the material. So this quantity can be measured and used for design purposes. Next, we studied the expression for stress intensity factor, which is valid only for the mathematically sharp crack. Next, we discussed that the stress intensity factor depends on the geometry of the cracked configuration. Thus, for the body with a through the thickness of the crack length 2a, the stress intensity factor is given as Ki equal to Y multiplied by S multiplied by root of PA, where Y is a factor which depends on the dimension of the sample and the loading geometry. The stress intensity factor can be used for design purposes by first determining the distribution of the crack sizes in a body by non-destructive testing. So the R curve need not always be independent of the crack length. When there are energy dissipating processes occurring ahead of the crack tip, then R may increase as the crack advances. This is especially true if the volume in which these processes are occurring is also increasing with the crack length. So the stress intensity factor or the fracture toughness can be determined by several methods. The 3-point bend test and the indentation method for fracture toughness measurements are described. As the crack size in a sample they are distributed, the fracture strength values of a group of samples of material are also distributed. So a distribution called the Weibull distribution is used to analyze the fracture strength data and extract the useful parameters of the distribution. Thank you.